Cool. So this was kind of a perfect tee up from Maxime and Guillaume to start talking about the kernel circuit. And the reason is because Noir function execution kind of directly plays into the kernel. Its outputs go directly to the kernel. And so I'll, in one slide, just talk about execution of an Noir function, which we just got a whole presentation on. And then we'll talk about the kernel, what is it, why is it, when kernel, and then dive into like the details of it, and specifically go through the private kernel circuit in the context of contract deployment, and then this will tie into Suyash's talk on roll-up circuits next week. Executing an OR function, quick review. So essentially, you have this Noir code. It compiles down to ACIR opcodes, and you execute each opcode. When a nested function gets called, you need to jump to that function. When a nested contract function gets called, you need to jump to that function and run its full execution. When you reach an opcode that needs some data from like our world state, like private data from the tree, for example, you're going to make a call to an oracle for injection of that intermediate data. And then ultimately you end up generating a proof of execution of that Noir function, which will be sent to the kernel circuit. And you'll also finalize some other outputs that'll be sent to the kernel circuit. So the actual kernel circuit, let's dive in. What is a kernel? It's corn. Not really. But anyway, so it's essentially, in general software terms, a kernel is a software layer between user code and the CPU and hardware. So it's a piece of code that essentially enforces execution rules and chooses which apps can actually run on the CPU. It manages resource access and allows cross-app communication, and it honestly does a whole lot more, but I'm trying to draw parallels here between a kernel and the kernel circuit in Aztec 3, which is a circuit layer between user code, which is Noir contracts, and the Aztec 3 rollup. It enforces code deployment and execution rules and manages access to data and from our trees and other functions within a contract. It also maintains some privacy of information, which is kind of related to, kind of along the lines of resource access. Okay, so but why do we need a private kernel circuit? Well, number one thing is for privacy, but Noir kind of already gives us that, which is mostly true, but we actually want privacy of the function that the user called in the first place. And there are some other privacy concerns that we'll come back to in the next slide. But for now, another thing that we need the kernel circuit for is composability. Functions should be able to call others and even those in other contracts. So what that means is that when Noir is used in the context of smart contracts, every contract function is going to be its own ZK circuit that can generate its own proofs. So that presents a problem because that means that one transaction can actually result in multiple proofs. So if a user calls function A in a smart contract and that calls B, which calls C, and they could be in the same contract or different ones, each function call has its own circuit and therefore will be generating its own proofs. So the problem is who combines them and how. And you might think, well, the sequencer could just combine them, but then that brings us back to the privacy issue. So what if function A calls B and passes some sensitive information to B? Well, the sensitive information shared between A and B should not be shared with the sequencer. So in this example on the right, there's some secret, and it's passed to function A, and function A then calls B and passes that same secret. B actually even returns a new secret. And so there's these pieces of information that are sensitive that link A and B. And so if the sequencer was to handle this, then they'd have to have some way of knowing that A and B link in this way, where like this secret is that critical information that links the two. And so that is kind of one of the main challenges that leads us to needing a private kernel circuit. So the kernel solves this, and it does so. Basically, the crux of it is that the user does this stitching together of functions, not the sequencer. The user runs this private kernel and generates the proofs. It generates the private kernel proof. It preserves the privacy of which function a user called, and it preserves the privacy of the secret information that links those two functions. And just kind of a note here, it does so by basically taking public inputs of the function circuits, like the individual Noir functions, and turning them into private inputs to the kernel. Regarding composability, every private function circuit in every contract in Aztec 3 follows the rules of the private kernel, which lets us verify and stitch together even cross-contract function calls. And lastly, a user only submits a single proof. Basically, the private kernel stitches together the nested function calls and the proofs generated by those nested function calls. And they're all stitched together. They're verified by the private kernel, and then a single proof that represents the full execution of that call stack is submitted to the transaction pool and ultimately picked up by a sequencer. So I'll do like kind of a high level recap before I move on, before we like really dive into the weeds, which is that user generates the private kernel proof in their browser. It preserves privacy of the user sending the actual transaction request. It preserves privacy of the function arguments and return values, even when those are between nested function calls. It preserves privacy of state reads. So anytime you need to go and read a private data note, it actually will be able to preserve privacy of which commitment was read from the tree, even if that commitment itself can't be, it means nothing to somebody. It still even preserves like which note you grabbed from the tree. And it preserves the privacy of the function itself. There's a caveat here, which is basically just that there will be a way to expose private information by basically passing it as arguments to a public function. But we have plans to try and make it that really obvious that you're doing that from a development perspective so that people don't do it by mistake. But it is important that we can do that for developing meaningful applications. And the last part, again, the user submits a single proof of the kernel circuit to the transaction pool.
Can I ask like a quick orienting question?
Sure.
So is this like a good example of how the kernel circuit would work? Is you have a private function f, you call it with some inputs that can be private, it produces an output called out, and then you want to plug out into another private function in a different contract where the input is like in, and the kernel circuit would demonstrate that out equals in.
Yep.
Okay. So it's kind of orchestrating like cross-contract execution. Is there anything more to it so far?
Or? That's mainly it. Is there anything more to basically the private kernel you're saying, like in general?
I'm just asking, like, so that's a good mental model to have in mind, like going for the rest of the talk.
Yes, that is a good mental model. It gives us this composability, and it does so in basically by proving that functions link to each other in a certain way, and proving that they all follow some standard rules such that they can fit into this one private kernel circuit.
Awesome, thank you.
Okay, so for each function in the call stack, the private kernel proves the following. It proves that the signed transaction request, so the actual request that the user signed, matches the first call in the stack. It proves that the function is in the function tree and that the contract is in the contracts tree. Basically just saying, yes, this function of this contract does actually exist on Aztec. And it proves that commitments referenced by the function call are actually present in the data tree. It then collects any new commitments, nullifiers, contracts, or messages that are created by this function. And then it verifies the previous kernel proof. So like this is recursive, which we'll kind of dig into next, but it verifies any like basically execution of the previous version of itself, and then says also, yes, the current function being processed, that proof is valid. So, all right, before I move on, does anybody have questions before we dig? I'm going to dive into like kind of the some of the data structures, and then we're going to go through examples.
So I wonder how you prove that the next function is the correct one. Like if your contract if you call the function A, which call function B, how do you prove that you called function B?
That's a great question, and I actually think that the next slide, hopefully, is it this one? Hopefully, I think maybe not this slide, but the next one, or like one of these next few slides with the data structures might answer that. So don't let me forget. We need to address basically how we prove that function A called function B, and we actually like followed that sequence properly in the kernel. So here's some of the inputs, and hopefully we'll get to. Hopefully this will help answer that. So the private kernel's inputs include the signed transaction requests, the previous kernel data, the kernel's recursive. So this is data essentially accumulated from previous iterations, as well as an actual proof of the previous iterations. And then we have this private call data, which is the data relevant to the function call currently being processed by the kernel. And so you can kind of see the data structures here on the bottom, although that's not, so if you guys want to dig further into this, I recommend you go and take a look at Mike's diagrams. So the previous kernel data is essentially the outputs generated by the previous iteration, and it includes, and it's a bunch of outputs from the previous iteration, as well as the proof of the previous iteration and the verification key. Now this is all empty or mocked for the first call to the kernel because there was no previous iteration. And so now, hopefully this should help answer that question, which is the private call data, which essentially is the information that is input to the kernel for the current function that this iteration of the kernel is processing. It contains the current call stack item, which is things like the contract address, the data about the function and the outputs of the function circuit. And it contains the private call stack for this function. So that is a piece of information. Again, this is information that is actually coming from the actual basically coming as an output of the app circuit. So the function circuit itself that was executed previously, we got a proof and we got some outputs of that like Noir function. One of the things that it will need to output is essentially what's my call stack. So like which functions, what is the current state of the call stack, meaning what functions need to be executed as a prerequisite for this current function being valid. And so that's kind of how we make sure that like if function A calls function B calls function C, that call stack is respected, is that each individual app circuit, each individual function proof will come with additional information, which is what's the context of its call in respect to like other functions that need to be proved alongside it. So does that kind of answer the question, Guillaume?
Yes, thank you.
Cool. So again, before I move on, this includes the proof from the function circuit and also the verification key, which the private kernel will use to make sure that the actual proof coming from the function is valid. Okay, so this is really just a diagram of all that because I just had a lot of words without very much visualization. So this kind of shows the recursive nature where you have this private kernel circuit. It's the same thing in each of these boxes. It takes the private circuits are on the right. These represent Noir function calls and the proofs generated by them. It takes that in, as well as in each iteration, it takes the proof from the previous kernel circuit. And so this kind of just shows that at each,
Yeah, so So in the first iteration, it would verify the signed transaction request and not the previous proof, because there is no previous proof. It's kind of like that it works. Because
Yeah.
it's the same. It has the proof as an input, but I assume that we are going to pass some random data at the first iteration.
Yeah, I think there'll essentially be a mock proof for the first iteration that will basically just be true, and there'll be some, like, we'll be able to detect, yes, this is the first iteration, and therefore a mock proof is fine, and then there's the additional check for that first iteration to make sure that the ECDSA signature matches the actual function that's currently being validated. There's also been discussion of actually, as a later optimization, having really 3 different versions of the kernel. The first one would be its own circuit that handles ECDSA signatures and doesn't verify a previous proof. And then there's kind of this intermediate one, or the recursive one that keeps calling itself, and then a final one. And the reason for that, I think the signature verification is actually expensive, and it's also expensive, or at least somewhat wasteful, to have that additional like mock verification when we could have that optimization.
Okay, thanks.
Okay. I am going to jump into an example with the call stack. I think a lot of you guys have probably seen some slides that Mike has done in the past on this. So I have a diagram on the next slide. Hopefully this won't be too overwhelming. So basically function A, let's say function A calls B and C. So function A will have its own call stack, which is basically B and C. That is inputs to the first kernel, and that first kernel we'll call kernel 0, which is processing function A. Will first verify the proof from function A, and then it'll take that B and C, that call stack from A, and it'll put it into this call stack that essentially the kernel is going to keep track of. A running call stack that the kernel will keep track of, which will then also be used by the next iteration or recursion of the kernel. So the call stack here ends at B and C. It generates the kernel proof for this iteration, and it hands off that information along with a bunch of other information to the next iteration. And I see that Guillaume raised his hand, so I'll pause.
Yeah, thank you. So I wonder how you can generate a proof from function A if your function A is calling B and C and you have not processed B and C yet. So I guess you need the result of B and C to get to the execution of A, and therefore the proof of A.
Yeah, so so I'll do my best to explain this, and I might tag somebody in to help me. But I think the idea is that when you get to the point where you're executing the kernel, all of the functions and their individual proofs of execution with all of their inputs have already been completed. Right? They've already gone through everything that we talked about in the last presentation, and their inputs have already been computed. And some of those inputs, or I guess some of their outputs, I guess we mix up those two terms sometimes in the ZK world, it seems. The outputs of those proofs will be the actual call stack. So alongside function A's proof, we'll actually get its call stack as an output. So you can prove that function A executed correctly, get its call stack, and then you hand that into the kernel. Now, what it's responsible for doing is at each stage, each time you go from like one kernel to the next. So you see here on the left, there's no verification that the kernel stack necessarily links to the next one. But now in kernel 1, on the right, when we're processing function B, it's going to pop an item off the kernel call stack, which comes from the previous iteration. And we're going to see that it's B, and we're going to make sure that it actually matches the function that's currently being processed by the kernel. So it's the idea that we're essentially staging a bunch of information for all 3 of these kernel iterations before we actually run them. And some of that information includes the call stack for each iteration. And we make sure that essentially the call stack that's dynamically maintained throughout execution of this like iterative kernel matches the original call stacks coming from each individual function. Does that make sense?
Yes, totally. Thank you.
Sure. So kernel 1 processes B. It makes sure that, like I just said, the item that comes off of the call stack that we got from the previous iteration matches B, verifies the proof for B, which again comes from the Noir function. And there's nothing to add to the call stack because B doesn't call any functions. So in the information we get from processing B before this, there was no call stack, so we don't add anything there. So now the call stack becomes C, and we generate the kernel proof for this iteration. And then we do the same thing with C. And at the end of C, there's nothing left in the kernel call stack. So the proof that we generate for this last kernel is actually the final kernel proof, and that's what ends up being submitted to the transaction pool and ultimately picked up by sequencers. And so this is just a little visualization that Mike has used in previous presentations. And so here on the right, we have function 1 calls function 2.1 and 2.2, and where these are different contracts. And I wouldn't worry too much about the public versus private for now. But basically, you can see that we have this call stack that kind of gets, it keeps changing throughout based on whether or not the function currently being processed actually made any nested calls. And this call stack keeps reducing in size as we process a function, but each time a function gets encountered that has an existing call stack, well, we have to then populate the call stack with that information, and we keep going until there's nothing left to process. Okay. I guess any questions before we move on to kind of the contract deployment example? Cool. So in the context of basic contract deployment, which is what we're doing for milestone 1.1, we basically want to do the following. We want to ensure that the verification key hash in this, so a transaction request is going to have a verification key hash. We want to make sure that it matches the VK of the constructor, right? So let me take a step back. Every contract is going to have a constructor, which is a function, a Noir function that will be called when a contract is deployed. And it can do a handful of different things. It can set up the function, set up the contract, maybe set some state. I think eventually we might have it be able to call other functions even, but either way, we're just saying this is a special function, but it does have a VK. It does need to be proved. So we want to make sure that the transaction request actually has that VK for the constructor. We generate a contract address and its nullifier. So the contract address comes from things like the developer address, the function tree root, some information about the constructor, and then also a salt, where the salt is just extra information that maybe lets you have a little bit of control over what your contract address looks like. Next, you have this contract address nullifier, which is probably just a hash of the contract address that gets thrown into the nullifier tree at some later stage, not as part of the kernel, just to make sure that nobody can reuse that same contract address. And then we generate some new contract data, which ultimately will end up being the information we put into the contracts tree. So that'll be things like contract address, the portal contract address, and then the function tree root, which essentially represents all of the functions in the contract. And it's, again, at some later stage, like in the roll-up circuit stage, that's when that information will actually be inserted into the contracts tree. And lastly, we verify the constructor function proof against its verification key. And sorry, maybe that bullet doesn't belong under this one, but we then, I guess it kind of does, yeah. So we use ZK snark recursion, which makes it possible to do, I kind of should have mentioned this earlier, makes it possible to have these like proofs that are verified by proofs. And then, of course, just like before, we generate one proof for this. So this slide, take a big step back, is what the private kernel does in the context of basic contract deployment. So at the very end of this, a kernel proof is generated that represents the contract deployment, the constructor call for this new contract. So the last things I wanted to mention is some things that the private kernel doesn't do, which is it doesn't execute the function circuits themselves. This is done prior, which is kind of the whole presentation we just had. It does not perform tree insertions for data commitments, nullifiers, contract leaves. That's all done later. And it does not merge separate transactions. It only merges, it only essentially stitches together nested function calls for the same transaction. And that's mainly it. And then I pretty much just have this one slide that's kind of teeing it up for Suyash next week. Basically, Aztec.js, what happens after this? Aztec.js returns the final kernel proof back to the user, represents the whole transaction. And they basically can then choose, do I want to send this out to the transaction pool? If they do, the ARS, which is the Aztec RPC server, will send it to the transaction pool. The user will get a transaction receipt. The sequencer will collect private kernel proofs from the transaction pool. It'll execute any public transaction requests, or at least generate or delegate the public kernel proof, which we haven't talked about, to provers. It'll order a bunch of the kernel proofs, and then it'll use that ordering, especially for things like tree insertions, where ordering may be important, to generate a bunch of inputs to the base roll-up circuits, which are the next thing that Suyash will be talking about next week. And then it'll submit the kernel proofs to those provers, which will merge them incrementally to one single, final route that we end up submitting as our roll-up to Ethereum. And that is it. So yeah. Love to discuss if you guys have questions.
I have one question about the roots of the trees that are used inside the functions. Are those going to be fixed across all kernel recursion, like constant every time you refer to the same old nullifier tree root, for example?
Okay, I went to a slide that's actually not relevant. But anyway, so you're saying basically, will the root of a tree, for example, like the nullifier tree, end up being fixed? So are you saying fixed between
iterations of the
iteration to the next?
Mhm.
I'm actually
Yes.
not sure.
Oh, sorry. Yeah. So initially it will be. Yeah. It makes the kernel circuit have fewer constraints. If you recurse through it 300 times, that's a terrible example. 20 times, yeah, we'll just use the same. We'll refer to the same commitment tree route, same nullify tree route all the way through. Maybe in future we realize we should generalize it, but for now that's good enough. Yeah, it just simplifies the code.
Yeah, so like when we are generating all the witnesses, all the proofs for the private functions, we must fix and one nullifier tree root, for example, and use always that for fetching from the Oracle, so we can have this only one fixed root when proving with the kernel circuit, right?
Yes. So it is an important point. Yeah, if you begin executing a function in the ACVM, we probably want to pause automatic updates of our database so we don't accidentally, overwrite the route that we're referring to or something like that. So yeah, it's a good question, something to be aware of with this, keeping just one of them.
Thank you.
Yeah, so I brought up here so anybody, I'm sure you guys have all been looking at this, but this diagram is super helpful. Thanks, Mike. So here we have this is the information here that essentially gets passed between iterations. And one of the things here is this constants entry. And in the constants entry, we have the tree roots. Essentially, I think by old tree roots, we essentially mean they are the tree roots before execution of these functions, not like after insertions. Yeah.
Can we get the link to that diagram?
Sure, and I think just for Mike's benefit, I want to mention that please don't edit the diagram without contacting Mike, because this diagram is his baby, which I think it says that word for word at the top of the diagram.
Sorry, I want to follow up on Alvaro's question to make sure I understood. So this means that if function A calls function B and function A makes any sort of state modification, function B is not going to be able to see those changes because they are all referring to the same tree roots.
I can take this maybe.
Yeah,
I've been
that's-
yes. So that's kind of in the current model for the kind of hackathon offsite. That's the case. That's not the kind of end state. So in the current model, you'd rely on a very fast Aztec block time to have those changes. The document on HackMD that kind of tries to kind of like tackle this question. You can see it here, and basically we need pending commitments. So as you put kind of new commitments into the tree, you could also add those to the kernel circuit context, so that you could either have an actual commitment that's in the data tree or one that somewhere in your execution trace was created, and the kernel circuit could kind of do the magic to work out like, was that pending commitment actually kind of created somewhere in one of its previous kind of iterations, and if so, it could kind of let you proceed and ignore the check. So if you go down a little bit, there's some like diagrams that try and explain it, but it gets quite complicated. So but yeah, it's something we'd have to add on kind of probably post offsite to the kernel circuit once we've got this working, because otherwise you end up in a bad state in terms of usability.
Makes sense. Thanks, Joe.
Yeah, thanks for the answer.
Maybe you could explain why, like, because another solution would be to say, like, if I have A that calls B and C, I could inline B and C inside A and just have one proof on one call. So why are not we following this road?
Sure. So I think the answer to your question is mainly composability between contracts, and like if you only had the context of a single contract, then you could say, let's just say we want to compile essentially using a similar way we already do today with like Noir executables. We want to compile like a single executable or a single circuit for each possible configuration of function calls in that one contract. But I think the problem becomes like when you want to enable basically any configuration of nested calls across like the entirety of all contracts deployed on Aztec, and the ability to essentially like verify all those calls. Well, each of them needs to have like, you need to have some information like a verification key that you can use to verify that one function in one contract is valid. That way you can make sure that to when you stitch them together, that not only were they stitched together in a valid way, but also that each individual circuit executed on its own and properly. Does that answer the question?
Not really, because you can do that when you generate the verification key for the big A, that is the inline A. You can do that at that time, so it's not a good reason, I would say.
I can jump in on this. So I think, sorry if I don't want to contradict anything. So sorry if I'm missing context, but I do think that it's possible to, like when you're compiling your contract, to stitch multiple function calls together as independent, like effectively independent functions, with their own verification key. But we still need to spec that out, because obviously, like if your contract has 20 functions, then you can't create a verification key for each possible like permutation of function calls that you could potentially make. But for common code paths, you absolutely could. Does that make sense? So like if you have a function which calls another function which calls another function within your contract, then I would expect the verification key to contain a circuit that executes all of those function calls.
Yes.
And that would then just be one iteration of the kernel circuit. If that makes sense.
Yes, that makes sense, but I don't see the problem with that. I mean,
Yeah, no, I think it will work. Sorry, let me just so I'm kind of thinking about this on the fly, but because our programs don't have control flow, like in terms of our once you compile the programs to a circuit, there is no control flow. So if you have a function that calls another function that calls another function, you can just treat that as one big function when you compile it, which I suspect we will end up doing.
But I guess the reason we still need the kernel circuit complexity is you can have functions deployed to separate contracts, and then you absolutely need distinct function calls and looping through the kernel circuit, because they've been compiled by different people at different times and deployed to different places.
Absolutely, that's the main purpose of the kernel circuit. Yeah, it's to compose function calls across the contract boundaries.
And that might even be dynamic, like based on arguments. You cannot have this control flow inside one circuit, but the kernel circuit allows you to have this sort of control flow by controlling which function you are calling in another contract by the arguments, for example.
don't think so. Because if you have control flow and you call to, like if you have if and I call B, else I call C, then you will have B and C on your call stack anyway.
No, you can add one of B or C, you can add B or C onto your call stack.
Yeah, you need both.
No, you don't. No, as in if you think about a function call where there's a condition which will either call function B or function C. In that circuit, what you'll do is that circuit will push one item onto the function call stack, and the address of the destination of that call that will be a witness value that changes depending on the predicate value to be either contract B or contract C.
And then the dispatching is done by the kernel. That way, you can get this sort of control flow.
So the pattern, I think, would be done within the user circuit. So the idea is what the kernel circuit is going to be doing is it's going to extract the public inputs of the user circuit, and some of those public inputs are going to be like additional calls to make. And so so there'll be some public inputs will be like the address of the call to make and the input parameters of the call to make, and the number of calls to make. So in your user circuit, if you want to call either contracts B or C depending on a predicate, then what you'll do is you'll set your public inputs to say, well, I'm making one function call, and the address will be either B or C depending on the value of the predicate, and you can do the same with the parameter, the input parameters as well. Does that make sense? And Guillaume, does that make sense to you as well?
Yeah, absolutely. Then I understand your argument about the computing all the permutations. So it makes sense, and it will be much more performant this way. Yeah.
Any other questions? If not, we can, I guess, end a few minutes early.
Well, David, thank you very much for putting this together. This has been a fantastic presentation, and yeah, really, really nicely done.
Thank you, and thanks for thanks to Maxime and Guillaume for teeing me up perfectly for this one.